Good afternoon, everybody. So I'll be talking about Kubernetes today, the history of it all, the basics, and beyond. So before I start, I would love to see a show of hands. Who has heard of Kubernetes before? Right, quite a few. Anyone who has worked with Kubernetes before in a kind of professional setting? All right, a few less. Oh, perfect then. I think that makes a lot of sense then. All right, so the agenda for now. I'm going to talk a bit about the history of Kubernetes because I think it makes sense to kind of know where it all began and the reasoning and how the kind of history unfolded to where we are today. We'll talk about the basic concepts a little bit so you have an idea how that system works and what is it good for and what are like the building blocks of Kubernetes in general. And then we're going to talk about something more advanced but super interesting, I think, called service meshes, which allows you to do some kind of cool things in terms of Kubernetes and networking and applications. But before we start, I'm just going to talk a little bit about myself. So I'm Daniel. I'm born in Berlin. A while ago, the wall was still standing back then. And my parents actually fled across the wall into the west. And from there, I saw the wall fell down. And Berlin developed into what it is today. And one of those things is it's quite a vibrant startup hub, one of the bigger ones in Western Europe. I studied computer science, and I've worked the last decade or so as a systems engineer, mostly software engineer when I need to, but mostly as a systems engineer because I love kind of building things, building complex systems together. A couple of years ago, 6 years ago, I founded a data science company. We do data science as a service, and the name of that company is Contiamo, which is Italian for we count. And why do I tell you that? The reason for that is that without Kubernetes and without Docker, we couldn't really be doing what we are doing with Contiamo. So have a quick look at this sketch here. This is the kind of the high-level view of all of the components that make up the platform of Contiamo. And I'm not going to go into any of the details here because it doesn't really matter, but I want to show you just a few things. So one main part is data science notebooks. And for you who haven't heard of what is a data science notebook, it kind of looks like this. It's for data scientists that usually use Python in this kind of interactive, very visual way of kind of programming and visualizing data and also training models for machine learning and AI. So that is a core component of this platform. A second one is stateless functions. So stateless functions, also called functions as a service or serverless in a more modern term. You may have heard that AWS calls it Lambda, Google calls it Cloud Functions. It's just a way to deploy a little bit of code or a machine learning model into an endpoint and then serve HTTP requests from that. And the nice thing about stateless functions is you can scale them out really nicely and you don't really have to deal too much with the underlying infrastructure. And as I said, Docker and Kubernetes. So those two are the main building blocks that make the entire platform possible, and without it, we really wouldn't be able to do what we are doing. All right, so that being said, we are actually hosting on Google Cloud. We made that decision pretty early on, mostly because the interface was always a little bit cleaner, a little bit slicker than what AWS has, and the feature set is at least somewhat comparable. The special thing about Google Cloud is that at the very beginning, when people were starting to work with Kubernetes, they already had a managed solution called GKE, which is called Google Container Engine or Google Kubernetes Engine these days. Using a managed solution like that is nice because you can keep the operational overhead in your company pretty low. So right now we have about 30 people, we have 2 ops people, and without having some sort of a managed Kubernetes service, this would be very difficult to do because administering and managing a cluster service like that manually is doable and can be fun, but it certainly requires quite a bit of manual effort. So that's why we use Google Cloud. We don't use Azure, we don't use AWS, so that's what we do. So let's skip to history for a moment. Hold on. Here we go. So where did Kubernetes come from? Where did it all start? So the year is 2006, so it's a while ago. Google engineers, sorry about that. Hold on. Here we go. Google engineers started programming a kernel module And the kernel module was called cgroups. And what cgroups allowed was, for the first time, fully isolating a process within a system so that the process was not able to use more resources than you would allow it to. So you could say, use only a certain amount of memory, use a certain amount of CPU, don't access certain resources like networking, or only have a particular narrow access onto things like disks. Before that, it wasn't really possible. Google engineers did that, also for their own purposes. And eventually, this feature, 2 years later, came into the mainline kernel and was basically promoted as a main feature of the main Linux kernel. And it kind of built the foundation of what is to come. Because without being able to isolate processes, you can't really have cloud computing. You can't really have modern orchestration. You can't really have Docker to begin with. So this was kind of like the first building block, the first foundation of what is to come. So, who has an idea what this is? Anyone? Maybe? So, just as a hint, I took this picture a couple of months ago in the Computer History Museum in the Silicon Valley. Here's a close-up of this. You can see it's a Pentium 2, so it's not the most modern system in the world. This is actually a Google machine. So in 1999, this is what Google looked like. They had these machines, commodity hardware, cheap hardware, bought in stores, nothing special, lots of them. Thousands, tens of thousands of these machines scaled out as a ginormous cluster. And so this is a rack from 99. And this is what, if you were to Google in 99, send something to Google, I don't know, what is the Matrix or something, this would respond to you. The reason why Google did that is because this stuff is cheap. If it breaks, and it breaks a lot, it doesn't matter. Because it's cheap, you just put something else in. But of course, you need to have a way of kind of organizing that, distributing that. And so in 2004, Google came up with something interesting, an internal development that they called Borg. Borg is their internal workload and application orchestration system. So they had these tens of thousands of machines worldwide, and they needed to have a way to kind of distribute their workloads, their queries, anything that they have across this ginormous pile of machines. And Borg is what they used for that. So it's a large-scale internal cluster management system. 4 years later, another kernel module came onto the scene. It was called Linux containers. And it's not just a kernel module, it's a little bit more than that. But 10 years ago, this is what came in. And what it allows is to do what's called namespacing. So we talked about cgroups before, a way of kind of isolating processes, giving them a particular set of resources. What Linux containers, it's called, allows you is to do namespacing, meaning you tell a process, or you enforce that a process can only see a particular subset of the system, can only see some processes, can only see some resources. So you basically build a little bit of a jail around a process. And it's also using cgroups to enforce that for resource consumption as well. So this is kind of the initial stepping stone of what eventually would become containers as they're used today. 2013, Omega came onto the scene. So Google continued the development process of Borg and really built it out into a new system that they called Omega. It was more flexible, it allowed to schedule more millions and millions of nodes, and it had all sorts of facilities that made it even more powerful than it was before. And then in the same year, finally, a company called .cloud, which was kind of like a mini competitor to AWS and Google Cloud, they came up with something that made using Linux containers a little bit easier. And the name of that company is Docker. And in that year, Docker saw an incredible amount of interest and adoption. So much, actually, that the company that was called .cloud before renamed itself to Docker, because everybody was interested in that. The reason for that is Docker containers are very much lightweight machines. They're easily usable. They have a nice tool chain attached to it, which Docker provided to build these images that are self-contained. And it allows you to ship your software as with shipping containers. You build it once, you ship it out, and it will always work. 2014, Kubernetes. Google uses all what they've learned with Borg and with Omega and releases onto the open source scene for the first time Kubernetes as a kind of an alpha, maybe beta version of it. In this year already, Microsoft, Red Hat, IBM, and also Docker joined the Kubernetes community. So from the very inception, you had a few bigger players that were immediately interested and kind of joined in. 2015, only 1 year later, Kubernetes was released in 1.0. At this point, the very first conference just around Kubernetes popped up in San Francisco. 2016, Kubernetes goes mainstream. So only 2 years after its inception, you saw a huge amount of adoption already in many, many startups and in some larger enterprises. Windows Server support came in. You saw more and more conferences all across the world evolving around Kubernetes, and something called the Helm Package Manager, which was introduced, which allowed you to really package complex applications even nicer and kind of deploy them into the system called Kubernetes. There were multiple larger case studies about Kubernetes. People and companies that use Kubernetes for really big things, and one of the more maybe commonly known one would be Pokemon Go, which in 2016 was this like lightning in a bottle, this spark that kind of went around the world and had everybody kind of go out into parks and stare at their phones, and they drove that with Kubernetes and wrote a super interesting white paper about it, about all the challenges that they kind of faced while doing that. So 1 year later, cloud and enterprise. Cloud meaning all the three big cloud providers, G-Cloud, AWS, and Azure, both had native Kubernetes support at that point. As I said earlier, Google Cloud started with that, and I would say still to this point they have the best support for that, but all of the three providers supported that. And also you saw enterprise adoption. So larger enterprises usually take a little bit longer to adopt new technologies, but 2017 was the year where even bigger multinational corporates started using Kubernetes in their own systems, in their own data centers. And this year, 2018, we see that adoption accelerates more and more. You see that Kubernetes is used more and more in bigger corporates. Some of our customers, also large telecommunications companies, they are very slow when it comes to adopting new stuff. And even they're now asking us, so about this Kubernetes stuff, can you help us install that in our systems? So it has finally arrived in the full mainstream. And you can also argue that in 2017, it won the orchestration war. So Kubernetes isn't the only system that does orchestration for applications. There's Mesos, for example, which is a famous one, and under the Apache Foundation. There's stuff like Yarn. So there are other kind of orchestration tools that kind of were running in parallel up until this point. But you could say that last year, Kubernetes kind of swept them aside, and everybody kind of focused onto only this one. So if you want to have orchestration like that, Kubernetes is probably one of the only choices you should go with. Future. So where is it going? It's now the end of 2018. So a few big topics are, one of them is serverless that I mentioned before. So functions as a service, AWS Lambda, cloud functions. Companies want to have that in their own systems. Small companies, big companies, doesn't matter. So Kubernetes is one way of achieving that, and it's becoming better and better to do this particular piece of functionality. Another one would be service meshes. I'm actually going to talk about that in a little bit, which is a way of programmatically changing the network and the routing between applications. And I'll tell you what that exactly means, but this will become more and more powerful and allow you to do much more resilient applications that are much wider scaled. All right, let's talk about some basics concepts. So I'm guessing every one of you has at least heard of or maybe even played around with containers and images. So that is a pretty common topic. It just means multiple containers can run into one machine, similar to a virtual machine, but a much thinner abstraction layer. You start with a base image, in this case Debian, and you add stuff to it. In this case, you add an editor to it, you add a web server to it. Each time you do that, another image is being created, another layer is being put on top of that, and in the end, that image, you spawn it as a container. At that point, it will be running, it will be serving your application, it will be listening and serving requests. So that is how containers and images work. You have all sorts of interesting tool chains to build these images. You have repositories to serve them from. You have versioning, all the things you do with regular applications, with regular code, you also have with images. And so that is kind of the main core building block for anything that kind of comes with orchestration. And what is orchestration to begin with? Well, now you can package these applications and you can run them on nodes and you can operate them properly. But when a node dies, when a server dies, your application is still dead. So you need to kind of move it somewhere else where it's healthy. You need to scale it out. If there's too much traffic coming in, if you're running a TV campaign or something and you have a super high spike in traffic, something needs to handle that load. And you can, of course, start preparing for that in advance, but ideally the system you're using will do that automatically for you. So that's what is an orchestrator. And it kind of looks like that. You have the nodes, the servers in a data center, and the orchestrator will make sure that your application containers will be scheduled where there is enough resources and will kind of replicate them in a way that it can handle your traffic. Now, in Kubernetes itself, the smallest building block that you can work with is called a pod. And a pod is, what is a pod? So, as I said, there is nothing smaller than that. A pod is kind of your application in a way. And inside of a pod, you can have certain things. One thing would be you can have storage. If you have a stateful application, you want to write something to disk, you need to have some sort of storage attached to it. So you have storage. You can have one or more containers running inside of a pod. The special thing about a pod is that all of these containers that run inside of a pod, they share the same network space. So whenever container 2 opens a port, container 1 can see that on localhost. So there's no external network communication necessary, and they all have access to the same storage. The special thing about a pod is that Kubernetes will start taking that pod if one of the servers dies and will move it somewhere else where it's healthy. And it will move the storage along with it, and it will keep these two containers together. So that is that. And of course, the containers interact with the storage, persist files, and then eventually maybe send something out to your customer, some request, response, whatever have you. Now, with most modern applications, you probably have somewhere a database, because you want to store your transactions, you want to kind of read something out, you want to persist something in a relational database. Now, what do you do now? C1, let's say, is your application. You want to communicate with the database. You can do that from within your application. You would open the connection to the database. You would make sure you have the right certificates in there, the right credentials, make sure that the network communication is sound, that the channel is secured. But that's a lot of work, and you don't really want to do that. You kind of want to just connect to localhost and hope that the rest is kind of secure. And normally, of course, you don't want to do that, but within a pod, it's possible. Assume C2 is just a database proxy. It will handle everything for you. It will do the communication. It will do the securing of the channel. And all you have to do in your main application, C1, is connect to localhost, and the proxy will do everything for you. And you have it all nicely packaged in this pod so that when one of your servers dies, or when you need more of these, Kubernetes will know how to replicate it in this exact setup. And it will really simplify the logic that you need to handle inside of your application. This is a very common pattern. It's called a sidecar pattern. You basically add a secondary container to your main application that handles certain functionalities for you that you don't necessarily want inside of your main application. Second thing we're going to talk about is a deployment, because now we do have a pod, we have our application, we have the communication that kind of works, but it's not running it anywhere. We have just defined it, what it should look like. We don't know how many of those are out there, where they should run, what kind of resources they have, and that's what a deployment is for. And like with anything in Kubernetes, you feed it a bit of YAML. Looks like that, it's kind of like JSON, human readable, and you just define a few things. You say, okay, what is it? This is a deployment. You tell it how many things of those do you want, what is the number? In this case, 3. If you have 1,000 servers, maybe you want 1,000, maybe you want 20,000. It depends, what your application is, what your traffic level is. And you define what kind of containers should be running inside. In this case, this whole thing is basically just spinning up an Nginx container, or an Nginx pod, with a particular version that listens to a particular port. Once you send this manifest to a Kubernetes cluster, it will know what to do. It will create the pod, it will start scaling it out 3 times, and we'll basically use this Nginx version that we defined down there with that particular port. Great, now we have an application, it's running inside of the cluster, it's resilient, when the server dies, doesn't matter, it will always spin up a new one. But the problem is, and this pod will even have an IP address, so each of them will have its own IP address. The problem is, if the pod dies, either this application crashes or the node crashes, well, Kubernetes will make sure that there are always 3 of them, but the IP will have changed. So how do we address that? How do we kind of, from a different application, how do we send a request to it? And for that, there's a concept called a service. And a service looks very similar to what we had in the deployment. It's just a bit of YAML, and all you define is what it is. It is a service. You give it a name, in this case, my service, which is kind of like a DNS name in a sense, and you tell it, okay, what are the ports? So we just defined in the deployment before, it's port 80, since it's the web server running there. But we also say, we give it a particular target port. So now what we can do is, whenever we send a request to my service, port 9376, it will find the right pod anywhere in that ginormous amount of machines, and will target port 80. So now we have a running application that is resilient, that can be rescheduled. We have a service, so we know how to address it, how to get to it. But now it's a web server, so we probably want to have some external traffic coming in. Right now, it's completely sealed inside of Kubernetes. So this is the last of the concepts that I'm going to talk about. It's called an ingress. And ingress is a fairly simple concept, really. Imagine you have your application scaled. Here you have 4 of them in various services, and you want your external users to be able to send something to it. You know, it could be a website, it could be a web application, it doesn't matter. And in ingress, it's just a way of opening up your cluster, put a little hole in it, and then send traffic through to your right service. And these manifests that I've shown you, you don't really want to manually write them and adjust them. Now, imagine you have, in a normal development flow, you have your development, you have your staging, you have your production. You don't want to really change these manifests for every environment. And maybe you have a complex application. It needs its own database. It needs multiple applications to work. You don't really want to just, copy and paste around these manifests. So that's where you use Helm. Helm is kind of a package manager. You define an application in a particular way. You define application templates, so these manifests that I've shown you, it will then replace certain fields depending on what you need your application to do. So that's what we can do. We define an application, what are the requirements, what does it need to connect to, does it need some storage, how often should it run? We actually run it. We define, okay, you need 5 gigabytes of memory on all of these nodes, find me some nodes that have it. If not, Kubernetes will tell you and will say, look, I cannot run your application unless you give me more resources. We are able to address the application. Other applications within the cluster are able to reach it now, and from the outside as well, because we are routing the traffic to it. So these are the main concepts. Once you've done that, you basically have something like that. An ocean of user containers, because you could potentially have thousands and thousands and millions even, depending on your organizational size, of these containers, of these applications running. And the Kubernetes master will make sure that they are evenly distributed to all of the machines in your data center that you have available. And machines can mean a virtual machine, it can mean a bare metal server somewhere, or it could mean your local laptop. It doesn't really matter. So that's cool. Now we have an application that is resilient. If something dies in your data center, it will be put back up. You can make sure that the right resources are being used. There's some security involved because the containers, they're very difficult to break out of. So that's all really nice. But we still have to write our applications in a particular way. And so let me give you a quick example here. Let's assume we have 2 services. We control these 2 services. Let's say service 1 just wants a cooking recipe from service 2. So easy. You just write an HTTP call to the service, pull the recipe down, done. Super simple. Now, there are some tricky things here, because you need to handle the endpoint. What does that mean? So you need to know, where do I actually go to send traffic to? Where do I send my request to? You can just send a request, hope for the best, hope the DNS resolution works, hope that the IP you get back will also work. But if it's high available service, you probably don't want to rely on that. So maybe you want to get a few DNS records back and then choose one and then send your request to that. What happens if that service doesn't work? You send something to it, it's super laggy, there's a huge response time, maybe it even breaks. What do? You probably want to retry that, okay? So go back into the code, add a bit of a retry logic. If then, kind of wait 20 milliseconds, maybe wait 200 seconds, wait an hour, try again, all of that logic, you kind of wrap that in there. Security. Let's say these are super secret, top secret recipes. You want to secure that. So maybe you add some authentication header to the service that you have to send along, some key. Okay, you need to handle that key in your application now. It's being loaded into memory. If your application is broken into, that key is going to be exposed. Not so great. Also, you need to have that whole handling in there. You need to set an HTTP header so that that whole thing is allowed to be pulled. Well, not so great. But it needs to be done. Same with logging. You want to know when something doesn't work. Let's say the request fails. You want to kind of spit out to standard out, I failed, the request failed, or the request worked, or the request failed for a particular reason. So that is also some logic you need to implement into your application logic. So now we already have endpoint handling. We need to retry stuff. We need to make sure security is right. We need to log stuff out. And then, of course, a more modern concept is tracing. Because as your application infrastructure gets more and more complex, you kind of want to know what happens on the way from your customer all the way to your application. So now you want to also have tracing in there, so you need to add that logic as well. So add a library to it, kind of do all of that. So what does that mean? From your simple application that just needs to kind of retrieve some recipes from a different endpoint, and all of a sudden we're here. We have to build all of these things onto it just to make sure that what we want to accomplish actually works. And that's kind of, it can suck. You can use libraries for that. You can be really clean with your code. But at the end of the day, wouldn't it be nice if we don't have to do that? And a solution to that would be what's called a service mesh. So a service mesh is kind of a new layer in between, and you can kind of think of it as a programmable network in a way. So what does that mean? So look at a kind of more modern microservice architecture. You have a whole bunch of services that run into your system, and let's say up there in the top left is where your request comes in from the ingress. Your customer sends you a request, and now it needs to kind of bounce around the entire infrastructure through multiple services back and forth until it eventually hits your application. And that is kind of actually what a modern microservice infrastructure looks like. So a request can take a particular path through through this particular network stack. And the applications that communicate with one another, they will just send out the request and hope for the best. Hopefully the network works. Hopefully we will find the right endpoint. And hopefully everything is secure, everything will work. But we don't really know. And we don't have a great centralized way of knowing. And it's difficult to manipulate what the traffic does and also kind of observe what it does. So one possible solution to this is called a service mesh, and it works in this particular way. So for this one here, I picked an example called Linkerd, which is one of the two service meshes I'm going to talk about. And it's using the Sidecar Pattern that we talked about in the beginning as well by adding a proxy to each of the pods. In this case, it's the Linkerd pod. And the Linkerd pods will now do all the communication for you. So all you have to do with your service is connect to localhost, connect to a particular name, and everything else will be taken care of. The proxies make sure that the communication is secure. The proxies make sure that the name resolution works, that you will always get a current name that you can address, a current DNS, if you will. And it will handle the entirety of networking. And so your microservice architecture, your microservice mesh will look like this eventually. So all the blue ones are the sidecars, and then they all communicate with one another. And you have now full control over them. You have an API you can use programmatically, and you can say, okay, I want my traffic to go this way. I want my traffic to go that way. I want to cut out certain parts. I want to make sure that everything is secure. I want to make sure that only certain things can communicate with one another, and I want to have a central point where I can see that. And a service mesh is what kind of allows you to do that. And there's some other neat things you can do. For example, think of this. You just deployed your new application and hope it works. A bunch of new features in there, really cool. This is down there. But now you switch that to live and everything breaks. Not great. So there are some ways you can work around that. There's a blue-green deployment where you clone your production infrastructure and you deploy your new application, you send your traffic over and oh, cool, it works. Great. If not, you roll it all back. But there's some better ways of doing that. For example, this one here. Only 5% of the live traffic now goes to your new version. The rest of the 95% stay with your old version of your application. If anything breaks, if you see a whole bunch of exceptions coming in, if you see users calling in saying, what's going on, okay, this didn't work. Take the 5% out, 100% goes to your old version, you go back to the commit and start fixing stuff. If the 5% work, fantastic. You increase to 25%, to 50%, eventually 100%, and now all of your traffic goes to your new version, and none of it goes to your older version anymore. The deployment is complete. Wonderful. Think of this, for example. Because everything now moves on the layer 7 of the application layer of the network stack, you have full control over everything. And you can read stuff out like the user agent. Is it an Android device that sends you traffic? Send it to these machines. Send it to these pods. Is it an iPhone? Send it to the Canary version, maybe to the new version we just deployed. So you have very fine-grained control over how you send traffic through a particular mesh, really. Another use case is kind of related to the one I talked about in the beginning. You have traffic coming in from the outside into your ingress. It goes through two services, and the last of the two services wants to make an outside request. It wants to pull a cooking recipe or whatever. And now we have the same problem that I talked about. What if this external endpoint is down? What if it's slow? What if it is laggy? In this case, you feed all of your outgoing traffic through the same service mesh as you do with the rest of your communication, and automatically it will work. If this service is down, it will automatically retry, depending on what you program. It will automatically find a different service with different recipes to kind of fulfill this request here. So you don't have to really care about any sort of making sure that this channel in the end here is secure, or that that it's available, because your service mesh will take care of it. There's some other cool things you can do. So imagine you have, as I said, this particular service mesh here. Everything kind of flows through. You have a great application. Everything works. Wonderful. Everything is great, always great when it works. But what if it doesn't? What if your applications start misbehaving? You don't know that yet. So when it starts happening, you're firefighting, you get the warnings at night, it's not so great. So now what we can do is we can tell the service mesh, take some of these services out. Just simulate taking them out of the entire network. How does it behave? So immediately you can see, you start kind of pulling cables out of the data center, if you will. You say, particular connections are now really laggy. You insert faults into it. You say, okay, this will now always abort. And you see how your application reacts inside of that. So you can kind of simulate a problem, even if there is none. And you can simulate that in a way that is secure, that is safe, because it's on your own terms. And you can immediately revert that back to what it was before. And I would call this kind of supercharged networking. And supercharged because it is kind of centralized. You can program it with API calls, even from your own application, and you have full control over everything that happens within your infrastructure. Security is a big point. The entire communication between the proxies is secure by default. So if you have some gRPC over HTTP2 connections that are usually TLS encrypted, you can do away with all of that and just do plain text. It doesn't matter to localhost, because the network itself will make sure everything is secure. And the third thing that I would like to talk about in the end is called observability. And a service mesh is something that allows you to do. Observability is a somewhat newer form of, you could argue, monitoring, but it is a superset of monitoring. It is a way of finding, like looking deep into a system and knowing at all times what is happening in each little bit of the whole chain. And one of those things is called distributed tracing. And I've talked about tracing before. I'll give you an example here. Look at this service mesh again, or this mesh of services, if you will. Now, let's assume a request comes in, and it will take a particular path through that network. You don't necessarily know what the path will be, because it depends on the routing. And you don't necessarily know what is happening in there, because maybe the second to last hop is the slow one. Maybe it takes a lot of time until it goes to the last one. But the customer doesn't see that. The customer only sees, okay, I'm sending my request out. It's slow. What is happening? And you don't know what's happening. So that's something where you can use tracing. If you look at this particular setup here, we go from A to B to C to D. And somewhere in the middle, we go to Redis to maybe offload some stuff, have it cached, whatever. We don't, if Redis is really slow, we suspect it's usually not slow, but let's assume it's slow. Then, of course, anything that comes out at the end of D will also be slow, but we don't know about that. Now, employing distributed tracing, all of a sudden it looks like this. So now, not only do we know how long each of these hops took, we also know things like how often was a particular function called, how much time did we actually spend in the cache. Is a particular function called way too often, something we didn't actually expect? Is traffic going over a particular hop too many times? Do we have a hot path in there that is overloading? All of these things we can kind of find out by using a service mesh. And introducing this kind of intelligent networking layer into your infrastructure, and it's easiest to do if you already have Kubernetes up and running, then this is a simple way, kind of, to have full control over how everything flows. You can secure it, you can monitor it, and you can programmatically change it from any point in your infrastructure. So there are two particular service meshes that are kind of big right now. One is called Istio. It's created by Google. And it is extremely powerful. It is a bit more complex to set up and operate, but you can do all sorts of things. All the things I've talked about you can do with Istio. And the second one I would urge you to try, if you want to try it out, is called Linkerd. It has a similar functionality as Istio, and it works in the same way, but it's a little easier to set up and to play around with. You will get up and running much quicker with Linkerd than with Istio, but both of those are amazing projects, and I think you will see those going forward quite a lot, because being able to change the networking layer and really elevate it up to your application eye to eye will really help kind of supercharge what you can do with your applications. Thank you.
Thank you for the great talk. I'm new to Kubernetes, and I have one question. Let's say that I have my infrastructure containerized already, and I'm running it with Kubernetes, like monitoring and all the stuff. But I definitely want to use Lambda in my architecture, and any kind of serverless, let's say, and I want to fit in there. And what can you say about this case? Can I integrate it to Kubernetes, or I must use it separately? For example, I'm using like AWS, and I should use Kubernetes separately and Lambda separately. How can I solve this case? And
right.
What can you suggest there?
It kind of depends on your architecture. It's, of course, if you already have stuff in Lambda and it's working and you have your functions deployed, there's no reason to not keep using them. From within your containerized applications, you can do your function calls to Lambda and you get your responses. They're usually going through TLS anyway, so they're secured, so you can continue using that. You will pay the price for it because Lambda will charge for that. What I would suggest you do, and it kind of depends on how big your project is using a project called OpenFaaS. So it's Open Function as a Service, which basically gives it the same functionality inside of your cluster. And then it's pretty easy to just move everything from Lambda into your own cluster. You don't pay extra money for it, but you get all the benefits for it.
Okay. Yeah, thank you.
Hello. I have a question. We have a project that has been hosted in raw Google Compute machines for years. And can you briefly explain, is it worth to migrate to Google containers or to Google application engine? We tried the last option, but it had a SSL issue. Did it fix it? We don't know. So maybe your expert advice will be very helpful on that. What is better, use Kubernetes as is or use application engine? For application has been hosted for on Google Compute,
right,
with load balancer.
Right. So if I understand correctly, you're using either a Google application engine, and you're asking if it makes sense to move these things onto Kubernetes, onto managed Kubernetes. It really depends on how much flexibility you want. If you're a lone developer and you have your little pet project, and it works on Google application engine, by all means, keep using that, because that's the simplest way. That's like using Heroku. It will be simpler. It will probably be even cheaper. But as you grow, as your applications become more complex, and you need to combine them and scale them out in a particular way, as everything becomes more complex, it makes more sense to go to Kubernetes because you have much more flexibility there. So it's hard to say for sure, but in general, I would say if it's a small application and you use it by yourself, keep using something like Heroku application engine. As soon as you get bigger, if you have a company and you have a production system, move to Kubernetes and really reap everything that they have.